In this session, we will be looking into the topic of feature extraction or feature analysis or feature engineering. It's a very key component of the machine learning framework. The idea here is that if you want to do any kind of pattern recognition or pattern classification in a machine learning application, you need to send the data, which is the signal in this case, into the digital system or the computer. But the signal cannot be sent as it is because of the large dimensionality of the signals. We call this as curse of dimensionality. So we need to do some form of a dimension reduction. In other words, reducing the size of the signal. For example, if the signal is of size 1 by n, where n is the number of time samples, we want to convert that into 1 by m features where m is far less than n. So feature extraction is some form of dimension reduction that helps in building very efficient machine learning models, because the models can learn the features and the system gets trained and it could be used for pattern classification, pattern recognition, or any artificial intelligence applications. So in this session, we will look into some key aspects of feature analysis for biomedical signals. And this will also be connected to the lab experiment on speech analysis. To start with, let's consider a toy example here. The idea here is to classify two groups of signal. One are the red signals, which are in class A, and the other one is the blue signals, which are in class B. The intention is to design a machine learning model which will classify the signals into either class A or class B. So let's assume we haven't got into the details of signal analysis or mathematics. We just know at this point how to get a simple mean, or standard deviation, or variance from a given signal, which is nothing but a vector. So if we were to extract two features, mean and variance for each of the signal, we will call this as features, and we will plot in a two-dimensional plot like what's been given there. Now what happens is that we will start to extract features from each of those 5 signals in class A and class B. So what has happened here is that in this toy example, it's pretty obvious when we extract the mean and variance of the 5 signals. Class B signals were above the line, and the class A signals were below the line. Okay. Very nice clustering and very nice distinction of the two groups. So now we can say we have trained the system, which is nothing but determining this classification vector, which is the line that separates the two groups. Now, in case of deploying the system in real world or in testing the system, we get an unknown signal, green signal. We will extract the mean and variance, and we see that particular signal is above the line. So now we can say this particular thing belongs to class B, because the system knows if it's above the line, it's class B. So here we have used simple mean and variance to design an ML model, which allows us to classify the two groups of signals into category A or B. Now, if you continue the toy example, there are situations in where the mean and variance may not be the optimal one. And for example, if you get features for different groups of class A and class B, something like this, then obviously a linear line will not be separating the groups A and B in an optimal way. So this leads to inseparable patterns with the two features that we extracted, mean and variance. And this will not work good when we were to send a brand new signal to test out what was the decision of that unknown signal, okay, because the training isn't successful. Now, why this system didn't do a good job. There could be many reasons. The one main reason is that maybe the inefficiency of the mean and variance in this particular toy example, which wasn't very discriminatory in terms of separating the two groups. So that's one possibility, is to change those features, or we could even expand the features. So one thing we could do is that the non-separable features which we had before, we could expand, adding another feature to the mean and variance. And in this particular example, we have picked up another feature called standard deviation, which is again related to variance. But let's assume now we have three features, which will be a three-dimensional plot. So the given signal now, which was not separable in the previous slide, gets separated in this particular example. Okay, so this was non-separable because we had only two features. The moment we expanded to three features, it was nicely separated. So this is all great. This is all great because this is the toy example, and we could see the separability, and also we can visualize the feature space. But in a lot of real-world applications, the thing that we don't know is that what kind of features one need to extract. What are the optimal number of features that one need to extract? So those are the unknowns, and this is where some background, some understanding of the signals will help you to pick the right feature combination for you. Okay, so in this toy example, yes, the three features worked, but in a lot of physiological signal analysis tasks, the feature extraction is still an ongoing area. There are a lot of very interesting features have been proposed. One such example is similar to what you have seen with the detection of the heart rate and the heart rate variability parameters using the Pan-Tompkins technique, where various features related to standard deviation of the NN interval and also other features related to the time domain variance were extracted, and we had summarized that heart rate variability features in the previous lecture. So that's one simple example of feature extraction that was done with ECG signal. But as I said, this by itself is a separate course, but we will see some highlights of feature extraction, both from time domain features and also from frequency domain feature analysis. Okay, so the very first thing is that with the human body, we understand the physiological system goes through a periodic or a cyclical behavior, which is great. And such a behavior leads to nice rhythmic signals. Okay, yes, like you go through nice variations when you're sleeping also, like you go through different sleep stages. So in all those cases, because of the human body being a very coupled system, you can get a nice rhythmic features. But the extraction of the features, just like any other thing, are made difficult because of various aspects attached to either the measurement things or related to other psychological and physiological variations. Okay, so nevertheless, we will look into how we can extract some rhythmic features, especially in signals like ECG, which show good rhythm. There are also other types of signal like speech. They also show some kind of rhythm behavior or periodic behavior. The first thing is that everybody is familiar with the idea of a dot product in vector notation. It's nothing but multiplying two signals, And if you have two continuous domain signals, this is how the expression is that. But in a discrete domain, we have the summation. But what we are coming at is defining the cross correlation function. As you have done before with autocorrelation, cross correlation function is defined as the signal, one signal multiplied with another signal with some shift. Tau is a shift here. Okay, so this is a cross correlation function in the continuous domain. We could get the same thing in the discrete domain. The only thing that changes is the summation sign and also the range of summation. So when you do the cross correlation with the signal itself, if y was xt itself, then xt plus tau would lead to what's called the ACF or autocorrelation function. And you're obviously experimenting the autocorrelation function in the speech analysis lab that you are currently involved with, where you're taking the autocorrelation function of the speech signal. So autocorrelation function and cross correlation function are considered to be a very good, simple representation for analyzing rhythmic features in a physiological signal. Okay, in cases where you have randomness involved, and many physiological signals have randomness because of the addition of the noise makes it random, and also the signal might go through some kind of a stochastic behavior, especially if there are process is kind of changing very dynamically. One good example is that if somebody's been given a CPR, then obviously your ECG signal is prone to go through a lot of dynamical variation. In such kind of a dynamical and randomness, we could always take the expectation operator, which replaces the sample average operator. Expectation operator is similar to the ensemble averaging that you have done in one of the previous labs, and the sample average, as you know, it's similar to a moving average. So as indicated before, the autocorrelation function tends to display peaks at intervals of any repeated pattern. So if you have a pattern repeating, the peaks in the autocorrelation function is a good feature that indicates there is a repetitive pattern in the signal. So again, it facilitates the detection of the rhythm, and it also can give multiple peaks, obviously, when the same event gets repeated in the signal throughout. Okay, so let's assume that there is one physiological impact in the signal, and that physiological interference tends to repeat over time. Then an autocorrelation function might be a good representation of picking up those periodic interference, and multiple peaks in that autocorrelation function will give that information for us. Okay. And again, cross correlation would allow us to find a common rhythm between two different signals. Okay, one good example is that typically in a lot of signal processing, especially with EEG, we get multiple channel, and if you want to know how one channel is related to the other channel, then cross correlation function comes in very handy. That also leads to another popular analysis called coherence analysis. Coherence analysis is more a frequency domain analysis. It's a frequency domain analysis, not in the time domain. It's in frequency domain. And it's pretty straightforward. What we do here is that we compute what's called the power spectral density. Power spectral density is nothing but the Fourier transform of the autocorrelation function. Okay, so if you have the autocorrelation function, you do the Fourier transform of the ACF, you do the Fourier transform, then you get the power spectral density. If you have the cross correlation function and you do a Fourier transform of that, you get the cross spectral density, CSD. Okay. Now, if you have the PSD, power spectral density, and the cross spectral density, then you can compute what's called the coherence spectrum. The coherence spectrum is given by delta XY, which is this function here, is nothing but the numerator, which is the CSD. So the numerator is the CSD, cross spectral density between the signal X and Y, divided by the power spectral density of signal X multiplied by the power spectral density of signal Y. The whole thing is square rooted. Okay, so very simple. The numerator is the cross power spectral CSD, and the denominator is the power spectral density of the individual signals. So if you have two channels or two different signals X and Y, if you want to know how much of the coherence is in them, then you have to go to the frequency domain, and it's all happening in the frequency domain. This is a good variable. This is especially useful, as I said, if you wanted to find out relationship between two channels, either in EEG or any other physiological signals. If you want to find out the relationship between two channels, how much of one channel information has been correlated with the other channel. You can also use cross correlation as a factor, but in many cases, coherence seems to be very efficient and also faster in terms of implementation. Okay, so it's really a powerful feature to know the relationship between two or more channels. The other feature, which is very simple, easy to compute, and quite powerful, is also called the zero crossing rate. Zero crossing rate is simply, it gives how many times your signal crosses the reference line, which tends to be the DC line here. Okay, so for example, if I take a sinusoidal waveform, in this case, it has crossed the zero line 2 times. Okay, this starts from here, so it's crossed it 2 times. In this case, the zero crossing rate is 2. Okay, and obviously, if the signal has a higher frequency, then the zero crossing rate will be higher. So it's an indirect measure of what's called the instantaneous frequency in a signal. Okay. It happens that this gives the busyness, how busy is your signal. Okay, so if your signal has a lot of activity going on, zero crossing rate tends to be pretty powerful. What happens here is that definitely this particular value could be impacted by the reference line or the DC bias line. So you got to make sure there's no baseline wander or low frequency artifact. If there are, then you know how to remove it by taking the derivative and you make the baseline 0 so that you can compute the zero crossing rate in a very effective way. So it's again a simple time domain feature. Zero crossing rate is a time domain feature. But as I said, it's giving an indirect measurement of the instantaneous frequency of the signal. Like, basically we are counting how many times the signal crosses a reference line, or in this case, a zero line. So ZCR has been used very much in speech analysis. It's been used in other acoustical analysis, like for example, in speech, it's used for detecting silence, appearance of silence. It can use for detecting voiced and unvoiced sounds, and I will come to that later, what voiced and unvoiced means. When you take another audio signals like a phonocardiogram, which is a heart sounds, it can be used for detecting murmurs. Okay, and murmurs might be pathological. It might indicate something wrong with the functioning of the heart. So zero crossing rate has been used as a feature. It's a number. It's just one number that will be used to do some kind of a machine learning to help in detecting murmurs, for example. Okay, ZCR is very, very efficient and very simple parameter. Going one step further, again in the time domain, we have a feature called form factor. Form factor is basically, in a high level, it gives a measure of the complexity of your signal, okay, in the time domain. So first of all, if you compute just the variance of a signal, variance of the signal is nothing but you take the mean and the standard deviation, square it. If you take the variance of a signal xn, we call that as activity. Okay, the parameter that's described, or the feature that's called, it's activity. Activity is nothing but the variance of the signal. So if a signal has a high activity, it means it has higher variance. Then you can compute what's called mobility. So the mobility, the definition of the mobility feature is that it's a ratio of the activity of the first derivative of the signal to the activity of the original signal. So what it indicates is that you take the variance of the first derivative of the signal here, variance of the first derivative of the signal, divided by the variance of the signal itself. Okay, so this is one layer above activity. So mobility is activity of the first derivative of the signal divided by the activity of the signal itself. In other words, variance of the derivative of the signal divided by the variance of the signal itself is the mobility. Now, a layer above mobility is the complexity factor, which is nothing but the form factor that we have been defining. So form factor tends to be the mobility of the first derivative of the signal to the mobility of the signal itself. So I'm going to be taking the mobility of the first derivative, which means if I take the mobility of the first derivative, then obviously what we get in the numerator is activity of the second derivative divided by the activity of the first derivative. Then when you take the mobility of the signal itself from the previous expression, we know in this numerator here, we have the activity of the first derivative divided by the activity of the signal itself. So we have these four quantities which will define the complexity of the signal or the form factor of the signal. Very simple, very simple. It's nothing but taking variance of the signal and its derivatives and putting them in a ratio will give you a numerical number, which is FF, form factor. And this is a very strong feature for machine learning applications. Especially form factor has been proven to be very successful features in doing a classification with EEG signals, electroencephalography signals, because EEG signals, unlike ECG, does not have a rhythm. It's not as rhythmic. So we cannot use a lot of the autocorrelation functions that we have seen before. Zero crossing rate might be to some extent successful, but what has been proven to be really successful, if you make sure that EEG signal is not that much noisy, then form factor is a good feature. Because if the signal is noisy, obviously the variance gets amplified and you might get a parameter which is biased, or a form factor which is kind of biased by those noise. But if you have an almost noise-free EEG, then form factor is an excellent feature which will be allowing you to classify different events, whether you want to classify epilepsy, or you wanted to classify stress level, mental task, or any other neurological disorders with EEG. take the EEG signal, do the form factor, send it to a simple machine learning, and you might get a nice separation of those features. Okay, so it's a very powerful feature, again, computed purely through time domain metrics. Now, switching the gear a little bit, I would like to take some practical examples and show the importance of feature analysis. So here I'm talking about the possibilities with speech analysis. Okay, speech analysis task. What are the possibilities? What are the things that have been done so far in speech analysis? So we can do all these things that are pointed out. You can kind of get an information about the age and gender, breathing aspects just from the speech data, cold, in some cases the crying of the infants, security application, depression, emotion state, and so forth. Okay, either it could be used for risk assessment, diagnosis, or monitoring, and you could see that there is kind of a nice tabular formulation of what things could be achieved by speech analysis in different applications. Okay, continuing on, you can expand speech to other sound, just like non-speech, for example. Okay, in many non-speech applications, for example, if you record the cough, we could do a diagnosis and monitoring of various disorders, including things like COVID-19. We could also get an understanding about cardiovascular disease from some acoustic signals, and so forth. So the many applications that could be possible just by doing an audio analysis. Audio includes both speech or non-speech. Okay? So this could be done even with your own available instrumentation. And in fact, I encourage you to do that, because in speech analysis lab, if you could record your own speech signals, you can do a feature extraction analysis, and it gives a much more solid understanding of the material that you're just seeing. So this is an audio file that I recorded through my own cell phone. And here you could see in this given 7 seconds duration, I've done a throat clearing, I have coughed, I have said the sound ah, then I've done inspiration and expiration for getting a respiratory signal. So all those different events I was able to record in a nice 7 seconds duration. Okay, and this could be done. So here you go. The data collection need not happen in a physical lab. It could be done from home. You could record these audio files, and it has profound impact, just like how we saw in the previous two tables, that it has a lot of applications. And again, it's very cost effective, it's cheap. It could be deployed in a mass, because pretty much most of the world's population have a cell phone. So it really opens up the domain of digital healthcare and connectivity in a very, very resource constrained context, and with wider applicability. Okay, so with that in mind, we will just zoom into speech analysis. Okay, so I showed in that couple of tables that you could do many things, but let's just zoom into speech analysis, which is also your lab 4 that you're involved with. In this thing, speech analysis, just like how we understood the mechanism of ECG signal generation, other physiological signal generation, speech production has been quite well understood. It's pretty much researched for many years. So we have very strong understanding of speech production and analysis and synthesis. That's why these days, pretty much you can see in most of the consumer electronics devices, there is some kind of a voice assistant or a speech interface that has kind of revolutionized the area of human-computer interaction. Okay, Alexa, Siri, Google Assistant, they're all classical examples where speech analysis has really had an impact in the day-to-day living. And this also applicable to people who need assistive technologies, who need rehabilitation framework. Speech plays a significant role there. Okay, so how does this work? It's pretty easy. It kind of connects to the filtering things that you saw before. Now we will see how that filtering is happening naturally in the human body. So what's shown here is that in the speech production system, there are 3 aspects. The input to the system, go back to the classical X, is kind of a pitch, a periodic pitch or periodic impulse train, like what you're seeing here. Okay, then obviously the output that we are coming out of the mouth is the voiced sound. In this case, I could call it Y. Okay, and you have seen this. This is nothing but H. The role of H is played by the vocal tract. So the vocal tract that we all have is kind of the filter here. Okay, so it's doing some kind of waveform shaping, a spectral waveform shaping of your input. So what happens is that in the case of the input spectrum, this is all in the frequency domain here. Input spectrum, it's more or less like it's flat. Okay, but if you see, that's separated by what we call the pitch period. Okay, what changes between different vowels a, u, I, o, u, and consonants and the male and female voice is the pitch. Okay, so the pitch period, if you can adjust, then obviously the spectrum will get adjusted, but it's more or less it's occupying the entire frequency band. But this vocal tract, which is acting as a filter, can do a selective bandpass filtering, for example, in this case, and we are getting the output when you multiply the H with the input spectrum, then you see that the output of the speech production system is something like that. So what it has done is that it has kind of done a bandpass filtering. Okay, and if you could also see, this could also be seen as a filter with 3 spectral peaks, and you know how to get this from your basic understanding of the pole zero placement. So maybe if I have 3 poles, I can easily model this system. Okay, so this is not something that is designed in a digital system or in a hardware or in a MATLAB. It's all happening naturally in the human body. It's acting like a filter. Okay, and this is what's happening now. So if you take a speech signal, if you plot it, you will see a spectral activity like that. Why that's coming is because of the input excitation that's given, and typically it's an impulse train with certain pitch period, and it all gets shaped by the vocal tract, and vocal tract is acting like a filter here. Okay, and that's what happens. And in some cases, your nasal cavity could also do some spectral shaping, but the dominant spectral shaping is done by the vocal tract. Now, if you look into certain vowels, like here I have taken the vowel A, just to give it the spectrum. So the x-axis is in frequency and the y-axis is amplitude of that in the logarithmic scale. And if you see this closely, you know, just the red thing, which is a spectral plot, you could easily see that the spectral plot has some kind of a periodic behavior. It shows your signal, original signal, also has some kind of periodic behavior. And all, in fact, all vowels, A, E, I, O, U, have periodic behavior. Okay, and if you take consonants, they tend to have more of aperiodic. They are not periodic. You know, so that's why we call A, E, I, O, U as voiced sounds, and anything else as unvoiced sounds. Okay, so in a voiced sound, what happens is that you do have what's called the fundamental frequency. The very first spectral peak is called the fundamental frequency F0. Okay, that's the fundamental frequency F0. Then while you plot the spectral envelope, so here the black line is just plotting the envelope of the spectral plot. When you plot that envelope, you will see the spectral envelope, few peaks, dominant peaks, and we call those as formants. So the F1, F2, and F3, if F0 is fundamental, are called formants. Okay, formants. Okay, F-O-R-M-A-N-T-S, formants. So very, very important. So in doing a machine learning with any speech application, whether we talk about the current voice assistant devices, they all extract these features and do a machine learning on that. So you need to extract fundamental frequency, and you need to extract the formats to do a feature extraction followed by machine learning. It becomes so important because now the entire speech signal, which probably is sampled at 8 kilohertz, sometimes even 16 kilohertz, and if you're looking at an audio, it's 44.1 kilohertz. So the entire signal has now been collapsed to dimension reduction into a selected number of features. Here in this case, it happens to be a fundamental frequency and the formats. Okay. Now, in the fundamental frequency, obviously, if you take F0, it does have what's called harmonics. Okay, harmonics. Okay. The harmonics are important, but what's more important is the shape of this harmonics, which leads to format. Okay. Now, how do we get these fundamental frequency and harmonics and the formats is the question. Okay. Now, if you look into the next graph, it's very obvious the vocal tract shape changes, and that's why you get different vowels. Okay, the vocal tract shape like this is giving you A. In the second case, such a vocal tract is giving you U and I. So when I plot in the frequency domain, this is in the frequency domain, the x-axis, 0 to 3 kilohertz. That's kind of the maximum intelligible speech that we have. In the case of A, we have three dominant formats. Okay, F1, F2, F3 are all here. Okay, in the case of U, there are again three formats, but the F1, F2, and F3 are here. If you take I, F1 is here, F2 is here, F3 is here. Okay. So in many machine learning applications, it's good enough to just see the first few formats. Okay, even F1 and F2 will do the job. So if you see, if I look into F1 and F2, they're at certain frequencies and they're at a certain ratio. This ratio will allow me to classify the different vowels. So if you take any A of any male speaker, for example, it will have a shape like this. If you take A of a female speaker, then yes, it will have a similar spectral shape, but the format ratio, in other words, F1, F2 ratio might be different. Okay. And the same thing applies to other vowels as well. Okay. So it's important to know that now you see that we are trying to develop a system which is starting to do a classification. It's starting to do an ML just by looking into the formats F and F2, in other words, format ratio F1 and F2. Now, what is missing in this analysis is F0. Okay. So many cases, it's very difficult to get the fundamental frequency. Okay. And unless you really do some kind of a spectral modification. So if you go back to the previous slide, to get this F0, what we got in the slide we just saw was this outer envelope of the spectrum. Okay, so we got F1, F2, and F3, but F0 is not always obvious. Okay, F0 is always not obvious. So the one way to extract F0 is we go through the time domain and we try to do an autocorrelation function in the time domain to get something called pitch. Okay, pitch information, and the pitch is nothing but manifested as F0. Okay, so that's how we do it. So that's why in your lab 4, yes, you're getting formats, but your F0 is not obvious in the spectral plot. So we have got an indirect marker of F0 through the autocorrelation function, ACF, autocorrelation function. Okay, so those autocorrelation function which reflects the pitch, and F1 and F2 will form your feature set. Now, what makes it different? The pitch is essentially coming because of your vocal cords, okay? The vocal cords that out here, the folds that are here, which is basically generates your fundamental frequency and pitch, okay? Fundamental frequency and pitch, and they are also responsible for the fundamental frequency and the harmonics. Your vocal tract, which is acting like a tube, the vocal tract. So this is vocal cords or vocal folds. Some people call it folds also. And this is tract. The tract is one that's acting like a filter. So the tract is nothing like a tube. Okay. So if you're playing musical instruments, the tract is very clear. Either you're playing a flute, it's kind of a uniform tube. It's uniformly shaped, but in case of the human vocal tract, obviously it's not uniform. That's what makes it very interesting, that we can have nice modulations, we can sing, we can produce all kind of variations and richness in the audio. Okay, so this vocal tract is acting like a resonator. All it's doing is that it's shaping, as we have seen before, your input excitation, which is coming through the cords. Okay, so the pitch, the F0 and the pitch is essentially because of your vocal cord. That's the excitation that's given. Whereas F1, F2, F3 is coming because of the property of the vocal tract, which is helping to act like a tube, and it's acting like a resonator, if you wanted to put it in the musical context. Okay, so it's just shaping your input spectrum. So fundamentally, F0 is important. F1, F2, 3 is just because of the vocal tract activity. Now, there are situations where people try to do speech synthesis and they don't worry about F0. If you're not using F0 in your speech reconstruction, if you're building a model for speech generation without F0, then that speech will sound more robotic. Okay, it will not have the melody. It will be very dull. It will sound more robotic. So that's why not a lot of times in the machine uh, generated voice, automated voice, you will find it much more robotic because of absence of F naught. So it also gives an idea that if you can tap into F naught, you can understand other aspects like the other subjective, the human aspects associated with speech, like emotion. Okay. Whereas F1, F2, F3 will allow you to classify, obviously, the various vowels, and it will allow you to understand what you spoke and things like that. So this is where the pitch becomes very important and a very dominant feature in extending your machine learning applications. Okay. So this is what you get to experiment in your lab 4 as well, where you will take 3 male and 3 female voices. You would do plots like that. You would extract features, which is pitch, F1 and F2. You will plot them and see how they're nicely clustered. Similar to the toy example I showed with the feature extraction, you will see what kind of a clustering is happening here. Now, this is an example, just like in the previous slide I showed, in the spectral plot with frequency in the x-axis, how the different vowels A, U, and I shows up. And they're very characteristic. This is pretty standard for all the human speech, okay, independent of the language, okay. So you do have vowels in other language too. So if you have something that's similar to or A, then you will have similar characteristic like what I've shown there. Now, moving on into other types of sounds, which are probably more biomedical aspect. Well, even with the speech, it's expanded to other domains, and I will come to an example with emotion later with speech. It's also used in understanding Parkinson's disease, because Parkinson's subject tend to have speech whose characteristics changes over the disease progression. Same thing, people are now using speech to understand dementia and Alzheimer. So speech does have a lot of applications in biomedical. Also to understand child development, a lot of children take a while to speak, and speech analysis becomes very important from a health context there. Snoring is again an important area. You all appreciate the snoring it makes some noise. The idea is that how would we analyze the snoring so that we can understand a very important health problem called sleep apnea? Because if somebody is having sleep apnea, they will snore, and that snoring, if it's worse, your apnea is bad. If your apnea is bad, means your body is not getting enough oxygen when you're sleeping. Okay, and it could lead to other things. It could lead to depression later if it's not treated. Apnea could lead into fatigue, drowsiness, accidents, so forth. Okay, so snoring sound is a serious topic in biomedical, and this is an example of a snoring sound analysis using the simple feature we just talked, time domain feature called zero crossing rate, where the snoring signal has been recorded through the microphone in the upper panel, and we just computed the energy in the second panel. By using zero crossing rate, we wanted to segment the signal, and the zero crossing rate is telling us, for example, where the segment boundaries are. Now, why it's important? It's important because rather than analyzing the whole signal, I would just take those points where zero crossing rate is pointing out to be a segment boundary, and I will just zoom into that, and I will start to extract other features like form factor, or even using some of the spectral plot features we talked in those segments. So that's what's happening. Now, as I indicated before, in addition to getting the health aspects of speech, we could also get the mental health or the emotional aspects of speech. Okay, and it's getting more and more popular because many patients these days don't go to the clinic. They do teleconsultation through remote monitoring in a virtual care setup with the doctors. And to understand whether this person is depressed or is the antidepressant that's been given is working or not, yes, you could do facial image analysis like how I have shown. The facial images point out to 6 groups of emotion: anger, surprise, disgust, fear, sadness, and happiness. So these are the 6 class, like just like how we saw 2 group classification, and also 2 group classification with speech, male and female. emotion could be classified into 6 groups, and this is defined by the psychologists. Now we could use, in addition to the images, we could use speech also as a feature. And I'm going to be playing a couple of speech samples for you.
Chinese! Me no Chinese, me Japanese!
So this is an example of somebody who's anger, and the speech is reflecting that. Now, on the other hand, if you take this happiness, it's pretty important to know. I mean, when I played these sounds, there's no speech aspect attached to that. But we know from the sound that you just heard, this person is happy. So these are non-speech clues. And this is where machine learning comes in very, very handy to understand such emotional states. And you can easily appreciate that, when we talk about babies, you are yet to talk, you want to understand whether their crying is good crying or bad crying. It's all about non-speech type audio that we are analyzing. And similar approaches comes in very important, especially feature extraction that I talked on analysis. For example, here in the speech-based emotion analysis, in the 6 groups category, what we have done is that we have taken the speech signals from the microphone and plotted them using what's called a time in the x-axis and frequency in the y-axis. Okay, so frequency in the y-axis, time in the x-axis. Now you could see this is the first format, this is the second format, and so forth. Okay, the first format frequency is changing over time with regards to the different emotion that's been shown. Now, if you see all the 6 maps, you could see this format ratio is starting to be different for the different emotion. So the formats which we talked just before need not be used only for classifying vowels and non-vowels, male or female. It could also be translated into a feature for recognizing emotions automatically. Okay, it becomes so important, and this area is called affective computing or human-computer interaction. The idea is that in many mental health and psychiatric contexts, this becomes so handy. And as I just said, it's really easy to do because you're just using a microphone, data to collect such information, and the role of machine learning is very, very significant here. Now, we will obviously expand on these topics of how do we really extract other features in a complex problem like emotion recognition as we go along in the course. But just to give an idea that, when we plot it simply by using this time and frequency mapping, and from just the concept we saw, like these formats are starting to really become very, very dominant, and they're starting to represent the different categories, especially from the 6 group emotion classification application. So with this, I hope you will be able to expand some of the things into the lab 4 and obviously into your project, because it's just starting to get into how do we extract interesting features from the signal to help the machine learning framework.